Hello and welcome to lecture 19 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to continue our study of the bands that we began last lecture, and then we're going to also define what is a semiconductor and take a look at the two charge carriers in semiconductors, free electrons and holes. Okay, so last time we took a look at how the orbitals of individual atoms evolve when many atoms are allowed to interact, forming a solid. So we looked at how these orbitals then form bands, which are regions where we can treat the orbitals as if they were forming a continuum. And we also learned that these bands could be fully occupied, partially occupied, or completely empty. Now in this lecture, we're going to take a look at the electrical properties of materials, analyzing each possible situation. So let's begin with an example where this band is fully occupied and this band is completely empty. So let's suppose that we have a material with these two bands, and these are the bands of interest. Now, suppose that we apply an electric field in this material. So what does the electric field do? Well, it exerts a force on the charge, on the electrons. And this force then accelerates the electrons. So the electric field increases the energy of the electrons because of the acceleration. Now, in this band, there are no electrons. So nothing can happen in this band. In this band, there are many electrons. All orbitals in this band are occupied. But when we try to accelerate the electrons, we're trying to increase its energy. But there is no orbital with higher energy for the electron to be accelerated into. For example, let's say that there's an orbital here, and you look at the electron in this orbital. So to accelerate it, we need to make this electron go to an orbital with higher energy. But the orbitals with higher energy are all fully occupied. And Pauli's exclusion principle forbids one orbital from having more than one electron. So when this electric field is applied, nothing happens to the material because the electrons cannot be accelerated, because there are no free orbitals for them to be accelerated into. So that means that a material with these characteristics is an insulator. There is no current when you apply an electric field because we cannot accelerate the electrons. There are no free orbitals for them to be accelerated into. Now, if we have this situation, we have this band, now when we apply an electric field, the electrons can go to orbitals with higher energies because now the band is only partially occupied. So in this case, the electrons can be accelerated, which means that there will be a current. So this material is a conductor. And if the material has these properties, we also have a conductor because the electrons in these orbitals, they will have free orbitals to be accelerated into, so they can contribute to the current. But the electrons filling these orbitals here, they will not contribute to current. So a material with these bands, it is a conductor because of these electrons. These electrons can contribute to current, but not this one. Now suppose that we have a material, and in this material, as the temperature goes to 0 Kelvin, the lower band becomes fully occupied and the top band becomes fully empty. So in this case, at 0 Kelvin, this material is obviously an insulator because there are only electrons in this band and there are no free orbitals for them to be accelerated into. But notice that I drew the energy difference between the two bands lower for this material than for the insulator. And I did that because in this class of materials, this energy difference is not so great, so that it allows a few electrons to be excited from this band into this band as the temperature increases. So as the temperature increases, the material is no longer an insulator because some electrons will be excited from this band to this band. Now this band is partially occupied, and this band is also partially occupied. So now there are free orbitals for the electrons to be accelerated into. So the material now conducts electricity, even though it's typically a very poor conductor. But it has characteristics of insulators, because it becomes an insulator at 0 Kelvin, and it also has characteristics of conductors, because it has some electrons that can contribute to current when the temperature increases. So this class of material is what we call a semiconductor. So by definition, a semiconductor is a material that, as the temperature approaches 0 Kelvin, the lower band becomes completely occupied and the top band completely empty. But typically, at higher temperatures, some electrons are excited from the lower to the top band due to thermal energy, so the material can conduct electricity because now there are free orbitals for the electrons to be accelerated into. Okay, so now let's define some important terminology. We've just seen that the electrons with energies lying within this band, they can contribute to current, so they can contribute to conduction, because there are free orbitals for them to be accelerated into. So this band is called a conduction band. Another important property is that the electrons in the conduction band, they interact very weakly with the underlying atomic structure. So they're essentially free to move about and contribute to the current. So these electrons are called free electrons. Now, as to this band here, this band is formed by the valence electrons of the atoms. So this band is called valence band. So this is the valence band. And the energy difference between the bottom of the conduction band and the top of the valence band is called a band gap. So the band gap is this energy difference. Notice that there are no orbitals with energies within the band gap. So sometimes this is also called the forbidden band, which means that there are no orbitals with this energy. So electrons cannot have energies within the band gap. Okay, so we have just mentioned that we have free electrons in the conduction band and that these free electrons contribute to current. Now what about the electrons in the valence band? We also have free orbitals in the valence band for the electrons to be accelerated into. So we should also expect that the electrons in the valence band contribute to current, and that this is true, but the way they contribute to current is a bit different than a free electron. So let's take a closer look at the electrons in the valence band now. Let's begin by considering the situation where the temperature goes to 0. So in this case, the valence band is completely occupied and the conduction band is completely empty. And the orbitals of the valence band, they are occupied by valence electrons of the individual atoms. So for example, silicon has 4 valence electrons, and I'm representing these valence electrons with these red balls here. And this big blue ball could represent the nucleus and all the other electrons other than the valence electrons. Okay, so these electrons are filling the orbitals in the valence band. So this is a geometrical representation and this is an energy representation. There are different representations of the same material. And remember that the material is electrically neutral. So if we count the number of electrons and the number of protons in a region, we're going to find that the total charge is 0. So the net charge is 0 because the material is not charged, it's not an ion, it's a neutral material. So we have here a number of electrons, a number of protons, and when we add these 4 electrons with all the electrons here and all the protons, we get that the net charge is 0. Now suppose that the temperature is increased. Now we know that some electrons of the valence band will be excited to the conduction band. So let's suppose that the electron that was filling this region has been excited to the conduction band. So recall that when the electron was still in the valence band, this region was electrically neutral, which means that the total charge, the net charge, was 0. But now the electron has been excited to the conduction band, which means that the electron is free to move around, so it goes somewhere else, it leaves this place, it leaves this region. If the region was neutral when we had the electron, it can no longer remain neutral when the electron went somewhere else. So what happens is now that we're going to have a positive net charge in this region. It is a local charge. The semiconductor is still neutral. If we sum the charge of electrons and protons in the semiconductor, we still get 0. But we have a local charge now in this region, local positive charge, because the electron that was in this region went somewhere else. Now suppose that we apply an electric field to this material. So let's suppose the electric field points to the right. Recall that the force that the field exerts in an electron is in the opposite direction because of the negative charge. So if we apply an electric field, the electric field will apply a force on the electrons, and now there are free orbitals. For example, the electron that was filling one of these orbitals was excited to the conduction band, so we have the orbital free. That means that another electron can fill the orbital that was vacated by this electron. For example, this electron here could now move to this region. And if it does that, then the positive charge would move to the right in the same direction of the electric field. So what actually moved was an electron. An electron went from right to left. But the net charge went from left to right because now it is this region that has a net positive charge. And the process goes on. So you have a movement of a positive charge in the same direction of the electric field. Now recall that an electric current makes reference to the movement of charges, not to the movement of the particles themselves, but to the movement of charges. We measure electric currents in units of amperes, which are units of coulomb per unit of time, and coulombs are the units of charge. So here we have a new type of charge transport. We have transport of a positive charge. So we have a new type of electric current. We have current due to the movement of a positive charge, as opposed to the movement of negative charge carried by free electrons. Now, this positive charge is due to the absence of an electron. But since the absence of electron is carrying a charge, we speak of this absence of an electron as if it were a real particle, which we call a hole. So strictly speaking, a hole is an absence of an electron. We can think of a hole as occupying an unoccupied orbital in the valence band. But since this absence of electron carries a charge, we treat it as if it were a real particle. We can even ascribe a mass to the hole. It would be the mass of electrons in the valence band. So we we speak of holes, we treat holes as if they were real particles carrying a positive charge with mass, momentum, energy, which are the mass, momentum, and energy of the electrons in the valence band. So we have two types of charge carriers. We have free electrons and we have holes. So to sum up, we have two types of charge carriers in semiconductors. We have free electrons, which are electrons in the conduction band, and they carry negative charge. And we have holes, which are an absence of electrons in the valence band, and they carry positive charge. So the electrical properties of semiconductors, they will depend on the concentration of free electrons and the concentration of holes. So we need to calculate these concentrations. And that's what we're going to do in the next lecture. So I see you there.